So yeah, I think the major push has been the environmental side. So traditionally, chemical engineers have
So,
been.
welcome back to the show, James Graves.
It's nice to be back.
Nice to have you. So, since we spoke last year, how has the chemical engineering industry changed?
How's it changed?
Yeah, so compared to when we last spoke, which was July of last year, how has the industry really changed at all? Because I was looking into some of the trends, and there's this massive push towards the environmental side of things with the chemical engineering industry. So I wondered if there has been any other developments.
So yeah, I think the major push has been the environmental side. So traditionally, chemical engineers have been sort of major or key workers in the oil and gas industry, which, like, obviously, as you know, contribute massively to climate change. And as the planet's trying to shift away to more sustainable energy sources, chemical engineering as an industry also has to adapt. So you're looking at certain technologies still to do with fossil fuels, so like carbon capture and storage, or some lower lower emission types of fuel, so including ethanol in your fuel to like keep the emissions lower. But then there's also transitioning over to new technologies such as hydrogen, electrolysis, renewable energies, more sustainable practices, more reuse, more recycling. Because as it becomes more important to take care of the planet, and as governments are putting in what I believe quite rightfully so, more ambitious climate and environmental goals, chemical engineers need to adapt sort of their roles to suit that. Now, obviously, there's still a big place for oil and gas. It's still a massive industry, petrochemicals, so making polymers, plastics from crude oil products, still a huge industry. But there has been a more noticeable shift away from that, and even within those industries, to more sustainable practices.
Yeah, I was going to bring up some of there's a couple of points there I want to touch on. With your last point about the plastics, I remember we use oil in our plastic packaging. And I remember you reminded me of this memory I had when I was 17, where I was just in my local, given my living situation at the time, I was in my local comic book store, and on the radio they said about, well, we could take some of the oil out of the plastics and reuse it at the
Uh,
time. Yeah.
yeah. So that's a process I believe is called pyrolysis, which is, but there are ways to get the oil out of plastic. However, it's the issue with a lot of these things is cost effectiveness. The oil is only worth X amount on the market, and it's quite a complicated and expensive process. So it's trying to find the economic middle ground between you want to reuse, recycle, take care of the planet, take care of people, but at the same time, it's a lot of money, a lot of energy to get that oil out from the plastic. So I think a lot of the push now, instead of doing that, is to less single-use plastic. So you don't have to worry about that plastic going to landfill sort of straight away, and less use of plastic in general, and then more sustainable types of plastic. So you can have plant-based polymers which are more biodegradable. So I think hemp's a big one for that, and sort of transitioning over to that really.
Yeah, because you reminded me, I can't remember if this was an actual product or concept, but we've had this problem in the oceans for the longest time with you chuck plastic, like you get a case of like alcohol beers, and it's not like in your typical energy drink cases where you got the cardboard boxes and plastic wrapped around it. Now you got like the six little. Well, there was I remember seeing this idea where it's not technically biodegradable, but turtles could eat them if they wanted to as a source of food.
Um, ye I am. I'll be honest. I can't say I know a whole lot about that, but there have been quite interesting work on making or like trying to genetically engineer bacteria or engineer plastic. So there's two ways. So one's trying to genetically engineer bacteria that can break down the plastics and make them biodegradable. There's quite a few interesting studies on that. I actually read a bit about it for my personal statement. It's still in the quite early stages of development and not ready for industry yet. And then you have the flip side, which is making the plastics themselves biodegradable. But both of those, because plastics are everywhere, like it's plastic on my laptop, my mouse, keyboard, like microphone, everything. Getting that transition over, it's one of those things that's going to take a long time, and it's trying to sustainably manage plastic production and plastic management in the meantime, really.
And there's also the incentives, which you mentioned earlier, from, say, the government, and to incentivize not just corporations, but people in general. So this was going to be my second point, which I alluded to earlier, where I currently live in, where I live is all electric. I pay for no gas because there's no gas. And long story short, didn't have hot water, got it back. But what the engineer told me was your landlords didn't have to hand this place over to me properly because without the gas. And I said to him, yeah, and that partly goes with the government incentive and initiatives there, where they're looking to pull away from gases and go to more, well, renewable sources of energy. Like with electricity, you got solar panels. It's just gone out of my head, but you know the one where you've got the buoys and the waves.
So tidal power or hydroelectric power.
Yeah, or the wind power. So that's kind of my point, because you need to have the incentives there as well for people to go, yes, we'll go down this path as well.
Yeah. So, yeah, there's been a concerted push by consecutive governments to obviously move away from CO2 emitting technologies anyway, but particularly in in a domestic application. So the removal of sort of traditional gas-fired boilers and the replacement with air source heat pumps. So the theory is, which is, I'm just guessing what you have at your house. So the theory is that if we decarbonize the electricity sector, so it's much less sort of carbon intensive. So for a kilowatt of energy, we're producing sort of 50-60% less CO2 than we were 20 years ago. So the idea is that if our electricity is low carbon intensive, then you got to move on to the next stage of what has a high carbon intensity, and that's heating our homes, because obviously I don't need to explain it to you, when you burn gas, CO2 comes off. And if you've got, say, 40-50 million houses in the country all using gas boilers, that's a lot of emissions. Now we've got to the point where heat pump technologies, so I'll go back a bit, there are two main problems with heat pump technologies initially. One was the noise. They were very loud initially, so they were only really used in industrial settings. So like in production plants and stuff like that, where like a radiator isn't applicable, you need like a whole room ventilated, and you don't really care about the noise. So you have these massive loud air source heat pumps powering these HVAC systems. And then two was the cost and availability. So they've been sort of tackled in two ways. So the cost and availability, there's now government grants and government laws that new builds must have air source heat pumps, and that there's a level of grant for replacing your boiler with an air source heat pump. Now, obviously, that's changed from government to government again. And then the technology, as with everything, as the technology improves, the product gets better. So now your average air source heat pump it's not louder than your fridge, which is a major technological advancement. So instead of it being to the point where it's detrimental to not just you but your neighbors, now you wouldn't even notice it in your day-to-day life. You probably don't. I'm guessing you don't notice your fridge making noise at all.
I do actually.
Yeah.
I do, but I know what you mean. It's not to the point where it's like, oh my word, I can't stand it. So I'll just be like, oh, the fridge is going off again. Okay.
Yeah, basically, yeah.
Yeah, you were saying about the tech with air source heat pumps, and you just instantly made me remember of a recent podcast I listened to of Chris Williamson, and I think I didn't really pay attention to the guy's name, but he basically runs a company that selects embryos. So do you know what that is?
Embryos as in...
No, embryo selection.
Or from fetuses, embryos. Yeah.
So for those who don't know, what the guy the guy that Chris was interviewing, what he does, he will you can run multiple tests in general for like autism, Down syndrome, arthritis, like all these genetic predispositions. And with embryo selection, you kind of select it, which ones you want your kids to have, which there's pros and cons. On the one hand, if you've got a condition that runs in the family, obviously you want to take that out. But if you've got a trait, but there's a bit of a caveat, maybe not. But he says that as more and more people buy, the tech gets cheaper and cheaper, and it's kind of the same with the air source heat pumps as well. Is the more that gets implemented, the cheaper it gets, and then the better the tech improves. It's the same with computers. When the first one came out, I don't know how much it cost, but look at them now.
We went over it in a lecture on Monday, but it's the idea. I really should remember this. Is so poor for me, but it's the idea that as technology gets more available and more used in wider industry, it's like a scale from 1 to 10. So 10, I don't know, it's like your light switch. Everyone uses it everywhere. It's been tested a million times, trillion times probably. We all know what it does. And 1 is like it only works. It's only been proven to work on a lab scale. It's never been used wider than that, but it has some potentially really big benefits. And then technology over time sort of graduates from 1 to about 10. So heat pumps are probably about 7 or an 8 now, whereas maybe even 5 years ago they were like a 4 or 5. Same with solar panels. So solar panels now are probably an 8 or a 9 technology, whereas when I was born, they were probably like a 1 or like a 2 or 3. Like they had uses in specific circumstances, and there was potential for them to be more widely used, but they hadn't been tested. They were still expensive, and it was overall a very risky endeavor. And it's when people are deciding on project management, sort of big engineering projects like capital projects, it's about weighing those two things up. Like how exciting could the technology be versus how proven it actually is.
What's that law where I forget what it's called, but it applies to computers where the next iteration outdoes the old one, but we've got to the point where it no longer applies because computers have become so advanced?
So
What's that called again?
I'm not sure if it's the same law, but it could be the law of diminishing returns, where
No, there's it's kind of like this is not the best example I know, but like Clare's law, it's got someone's actual name in it.
Can't say I'm familiar.
I'm not going to say their name, but we both know someone who would know. But yeah, kind of reminds me of that.
Yeah.
What have you learned? Well, you alluded to this earlier with the lecture with the tech where more people buy it becomes 1 to 10. What else have you learned over the past year from your uni course when it comes to chemical engineering?
So I would split it into 3 main categories. The first one's the X's and O's, which are like your principles of chemical engineering. So your heat transfer, your fluid flow through pipes, so your fluid mechanics, your reaction engineering, bioreaction engineering, sort of membranes and separation technologies, distillations, all of that stuff. So like the key principles you need to know to work as a chemical engineer. Then I'd say the second one is modeling. So you have all that information that you know. So you know how to do a mass balance, like certain mass goes in, reaction happens, certain mass will go out here, go out there, and you got to work out how that works safely. Then what I'm doing a lot more of now is modeling. So you've got that mass balance. How would you model that to scale up a reactor? So at the moment, I'm doing a water treatment plant. So we know that I can work out that we need this, and this equation for mass balances for oxygen, water, sort of microbes, and biomass. How do I take those equations and model them so that I can get the rough size I need for my reactor, the rough pressure differences I need to account for, the rough cost? That's sort of the second thing. So modeling the equations and applying them in real world factors. And then the third thing is the sort of more soft skill side of it. So your project management, your environmental impacts, the law, the sort of, and then sort of almost linked but not quite, the career development side. And I'd say those are sort of the three main categories that they've really focused on developing with us over the last year.
What are the principles of a chemical engineer? Because I didn't realize I could see principles of becomes like doctor, like health or law, but I didn't realize there's principles behind being a chemical engineer.
So the principles I'm talking about are more sort of technical principles. So they're not like, so there's obviously, we do morals and we do ethics, and those are important, but it's more sort of the basis for knowledge. So, like, one of the first things we learn in mass balances, which is incredibly simple when you say it out loud, but you always forget it, is mass in would be equal to mass in plus the generation and accumulation of mass will be equal to the mass out plus the consumption of mass. Like any, so if you have a reactor, any mass that goes in and is generated is equal to any mass that goes out and is consumed. And that's the sort of principles I'm talking about. And so I'm in my third year now. In the first year, they were sort of building those foundations for you. So they did it for mass, they did it for energy, which again, incredibly simple. Any energy that goes into a reactor plus any energy that is generated in the reactor must be equal to any energy that goes out of the reactor and any energy that is consumed by the reactor. And then those are sort of the two main foundations. And it's just sort of every year they've built upon that. So you had those as sort of your base principles, your first laws. Then second year they developed on it a little bit. And third year, it's sort of the advancement of those principles, really. And it all still pretty much boils back to those two main rules, but it's applying it across a wider range now, really.
Okay. Yeah, I didn't realize it was all technical.
Yeah.
But no, that makes sense. I suppose health and safety comes into it, which I was going to bring this up later, but sort of I've kind of we've brought it up. Well, I've brought it up now because I know earlier this year you were doing some work shutting down an entire plant, and I had a bit of a look into this. Go on.
No, go on.
I know I was looking into this a bit this yesterday evening, this morning, and I didn't realize. You alluded to this when we last spoke in person, but I didn't realize there was so many plans and regulations and health and safety procedures when it came to turning off the plans. Like, yeah, obviously you can't just flick off the off switch, otherwise you run the risk of Chernobyl. But I didn't realize there was just so much legislation in the way to turn down a plant. Yeah, obviously you're dealing with chemicals, and if you get it wrong, bad things happen. But what was it like to shut down an entire plant?
So, firstly, it's a very long process. So I was only there for a very short chunk of it, really. So they are still going through the shutdown now, trying to get approval for certain things. But so the work I was doing, it was in the pharmaceutical industry. And so it was shutting down an old production plant because they moved to a smaller, more efficient building, and the old building was costing too much. So so first there's government rules. So they had to keep it operating in what was essentially process conditions. So they weren't making any product, but they had to keep it in a condition where it could be used to make product initially, which was costing them millions a year. So my job, so I was hoping decommission that building. So it was so to keep it, they had to do temperature control, pH control, pressure control, all of that. So part of my job was to help isolate the utilities that were used for the control of those conditions. And that involved drafting up plans. But for everything you do, because the safety is paramount, especially when you're working with medicines and drugs, if you make a mistake and you contaminate a set of drugs, it's life-threatening, essentially. So you have to go through a procedure. So just for simple, so like for shutting off, say, the steam pipes, you needed to get the steam tested, like the valves you would use for shutdown tested. You'd need to, which would involve working with site engineers. You would need to draft up your isolation plans. You need to write an impact assessment. You need to then approved as an engineering change control, which was approving that they would change it. Then you need to change it. Then you need to do another impact assessment once you're done. And that was just for, say, shutting off a steam line. Now imagine you've got to do that for almost every bit of equipment, every utility, so water. Because, but yeah, no. So say like the point is that safety is like massively important because you might be able to cut corners and do it more quickly, but if you make a mistake on a steam line and you've not chosen the correct safety procedures so that you don't have the right valves here or there or wherever, and you've isolated it and the valve breaks, you have a giant gush of steam coming at like 2 or 3 times normal pressure at someone's face, and is so you have to. It's one of the things. So we had a safety module last year, and it's one of the most important things in chemical engineering, maintaining that level of safety. Because when you don't, you might get away with it for 1 day, 2 days, a month, a year maybe. But if it goes wrong eventually, it goes wrong in a disastrous way. And they showed us like countless examples of it, really.
What were the examples, just to digress a bit?
So the one that always sticks in my mind is the Buntsfield explosion. So it was way back, I think in the late 1960s. There was this chemical plant, and they had been doing inadequate safety checks for a while now. Some people had raised the alarms, but what really did it was they were supposed to have 4 tanks, and the product or whatever was supposed to go up and through one, up and through the next, up and through the third, up and through the fourth, and then out. One of the tanks malfunctioned. What should have happened was you shut it down, you fix it properly. But what they did was they put in a bypass on the tank with a valve and some pipe that wasn't built to deal with that level of pressure, essentially. So eventually the pressure builds and builds and builds. That valve, gasket, whatever, breaks. You have a massive hit of overpressure, and due to the other conditions around the plant and weather conditions and whatever, you have what's called the overpressure causes an explosion essentially, and the explosion reverberates for miles. So you've got people in the town over whose windows are cracking. You had people die on the site. It was like really disastrous, and it led to sort of a lot of the modern day safety procedures that we have now. But at times it seems extremely tedious. Like, do I really have to write an impact assessment for every single thing? But without that in place, people tend to cut corners, and cut corners cost lives.
Yeah, and then you've got the other problem of, like you said, with those who brought it up, as well, why wasn't something done sooner about it?
Yeah. So, yeah, because a lot of the accidents we went over were entirely preventable, and it was cost-cutting measures. So the other one was in Bhopal in India. They had the release of some toxic chemicals into the surrounding town, and it was entirely preventable. You had people raising the alarm for ages, like maintenance engineers, technicians, and due to sort of political factors, economic factors, foreign influence, nothing was done until it was too late for something to be done. And which is why there's such strict regulations in place, and why there's such an emphasis on safety and being a principled engineer, because you can cost lives.
Yeah, and then the blood's on your hands, which directly leads to what I want to ask next is, so you said that you learned about the principles of being a chemical engineer, how to build a reactor and the modeling. How does the theory work, translate and differ from the real world example of you aiding shutting down the pharmaceutical plant?
So I'd say the biggest link, I would say, is the diagrams. So one of the first things we learned was how to read, it's called a process and instrumentation diagram. So when you have a reactor or any building, it's basically a diagram showing you where all the pipelines are, where all the valves are, where all the reactor vessels are. And you can use that diagram to identify what valves you would need to shut off to isolate the system. So that was very similar. I've done that in class, saw the diagrams in person, and it was basically the same thing. I'd say the major difference is the level of paperwork and approval you need to get. So when I'm working at uni, I'm working on a project, and I'm saying I'd need to and I want to make a change to my system or whatever. The only person I have to ask is me and maybe my sort of course convener or whoever's in charge of the lecture. Whereas if you want to make a change on a plant, you've got to read over the sort of SOP, which is standard operating procedure, on how you would do it normally. You got to write, say, an isolation schedule, which is your plan for isolating. You've got to do SCREA, which is how it would impact the performance of the not just the plant but the site as a whole. You then have to get it tested. You then have to get it approved as an engineering change control. You'd have to explain where you drain down the system from. So like once you've isolated it, you've still got water in those pipes. So how are you going to get rid of that water in a safe manner? And all of those steps require paperwork, require a paper trail so that when I left, someone else who's never even heard about it can come in and go, oh, so they've done this, this, and that, and it aligns with the regulations and this, and that way. And for me to get from the point that I left it at to the end goal, I need to do X, Y, and Z using X, Y, and Z and fill out X, Y, and Z forms. And it's sort of, I'd say the main difference is the traceability of your work and the applicability of the safety. So obviously we do the theory side of safety, but it's the applicability of it, I'd say, was the main difference as well.
Okay, so it's real world practice, which is, yeah, because I've heard that as kind of a common theme with just any industry these days, where especially the one that came to mind was nurses. So I was having a conversation with my co-workers about this, and long story short, they just said to me, well, they were speaking to some of the older nurses and the newer nurses, and they said the newer nurses are like, we've got no idea what to do with being in the classroom all the time, and the older nurses saying the training is not what we're used to because we actually learned on the job. But then I get where you're going with this, because as dumb as it sounds, with all the examples you gave with the explosions, you can understand why. I never realized it was like, is it for every little tedious little thing, like you're saying with the water? I mean, obviously you're not going to flush it down the sink, but it's go on.
Yeah, no, it is. But so you essentially have two jobs. One is to do the engineering, and the other one's to do the paperwork and get approval in the most safe and efficient manner possible. So nobody, well, I'm not going to say nobody, but I would say the vast majority of the population doesn't want to sit down and do paperwork for sort of seven of their 8 hours of the day. So your secondary role is to basically, you have to do this, and you know how to do it safely. It's how can you do the least amount of paperwork while still maintaining the regulations and still keeping it safe. So if that means you have to do a couple extra bits of paperwork to make sure it's still safe, you do that. But if it means that you can say combine do 2 bits of paperwork, or you can fill out a shorter form, it's doing that as well.
Do you think the chemical engineering industry is going to get more complicated with the push towards a more environmentally friendly world, or do you think it's going to ease off a little? Because I've noticed this just as a general trend throughout the years. Well, when I was, say, I want to say 10, 11, things were a lot more straightforward, but fast forward to what? I'm 26 now. Everything, there's like you were saying with shutting off the steam, there's regulations for every single little thing. Do you see it getting a lot more kind of like Big Brother, in the sense where it's this constant surveillance, this constant watching over, making sure you're doing everything properly? Or is it going to, with everything getting, like, we're taking stuff out of, like, less gas, less carbon emissions, do you think it's going to get a bit easier?
I would say, as with most things, it will largely stay the same until there's a major incident which causes it to change. Now, I can't say for definite which way it will cause it to change, but if I was to hazard a guess, the way it normally works is you have the regulations in place. people get lax, get lazy with the regulations, something bad happens, then they'll tighten up the regulations more. And it's proven to be effective. We have less accidents now than you did 10 years ago, than they did 20 years ago, than they did 30 years ago. So I'd say it might become more stringent, which is a double-edged sword. So process of doing stuff is slower, but the process is also safer. So I'd say it will become more stringent, but I don't think that's necessarily a bad thing. I just think it's different.
Does that worry you at all, or does that bring you a sense of peace and calm?
Doesn't worry me overly. It might frustrate me at times, but it definitely doesn't worry me. I think when you're working, so even let's say not oil and gas or pharmaceuticals, when you're working in any sort of chemical engineering industry, you're working with reactions, potentially high temperatures, high pressures, that if they go wrong, could cause serious damage and serious harm to people. So I think it doesn't necessarily give me comfort, but I also understand the logic and the reasoning behind it. And I think while I might not agree with everything, I think I agree with enough that I'm willing to sort of not take issue with the stuff I disagree with, basically.
What are some of the stuff you disagree with then?
It's not a whole lot, actually. I wouldn't say necessarily disagree with. I think that might have been the wrong term. But when I was working, sort of getting approval for anything was really tedious and could get really frustrating. And you were sort of just like there, like, I hope this goes, because you'd have days where you were just almost sitting around waiting for stuff to happen. But yeah, so I wouldn't say disagree with the right word. I'd say sort of more find tedious. But I'm like that's something I very happily live with the trade-off that the processes as a whole now are significantly safer than they've ever been.
Oh, if something else major happens, it'll only get safer.
Yeah.
Yeah, but then there comes a caveat of you don't want to be in the middle of that mess when it goes down.
No, no.
Oh. Have you? Here's a question which I just came up with earlier, which I thought would be fun to ask. Would you ever consider running your own chemical engineering business? Because when I was doing my little research, I found I really should have written these down. Can you write them down? But I've seen some startup chemical engineering roles. One was doing stuff with water. I think another one was doing something with temperature, and they were all across the world. So would you consider doing a chemical engineering business yourself?
Uh, yeah, it'd definitely be a consideration. So, sort of two sort of areas of business you could do. So, one is the technologies you come up with yourself and the scaling it up and the selling the products, which is something that I'd find, like, from a design point of view, I would find insanely interesting to do, but it's also a lot of work. And then the other one is the consultancy side. So you set up a business as a consultant, you go in, you help with engineering problems, you do all of that. Now, I obviously, in a dream world, I would like to do one or both of those because I would like to work for myself, but it's not something that I'd also, in the right roles, I'd also be very happy working for a company, providing I find the work fulfilling or interesting, and it's a good role to work at and to develop my own skills, basically.
Okay, so you'd go either way then. You would, doesn't
Yeah,
matter.
yeah.
Okay.
I think it's more what I'm doing than whether I'm working for myself or who I'm working for. If I'm doing a role that I enjoy or I'm working for myself in a something that I find interesting or I'm passionate about, that for me is more important than being my own boss or having the security of a job. It's more the nature of the job than the factors around the job, basically.
So what would those factors be for you?
So pay is obviously one. I'm not going to beat around the bush. As much as I enjoy engineering at times, I don't think I enjoy anything enough to do it for free for the next 40 years or for low pay. But so then it's the work itself you're doing. So the engineering side, so the design process, the technical skills, the consulting, sort of how challenging is that? And then it's the company ethos, company values. What is the company actually doing? Is the technologies being made used to benefit people? Is it being used to help people? So I've had a look at like a lot of sort of water industry stuff, particularly in the developing world, because you're doing water treatment out there, you're being compensated quite well, but you're also helping people. It's hugely beneficial, and I find that quite fulfilling as well. So I'd say it's a combination of those things.
Yeah, and I don't mean to turn this into a negative conversation, but is there any industry that you wouldn't work in? Out of it could be principle, could be morals, could be ethics. So you'd happily work for a water treatment plant in India because it's helping people, but is there one where you just go, nah?
So I wouldn't say strictly no, I'd never work in an industry. However, I'm more hesitant to work for oil and gas companies whose only role is oil and gas. Now, if they're a wider energy company that encompasses, say, an oil and gas plant, I'd be happy to work on that oil and gas plant, but I'd be more hesitant to work for Shell at an oil refinery, for example. There, because of the environmental impacts, and pretty much every other industry, or like other stuff, like say weapons or an arms company, I'd be more hesitant to work. I wouldn't say I'd never work for them, because if there's obviously certain roles where you find them and you're like, that aligns with my personal values, but I'd be more hesitant and I'd have to research it better before I'd be willing to commit to those types of companies, basically.
Okay, so research first, supply later, and yeah.
Yeah.
Do you think the chemical engineering industry is, because I seen a statistic earlier where is the chemical engineering industry is due to grow by 9% come 2030. As someone who's studying it, do you see that A happening? And B, let's say I gave you the task of getting people into the industry to meet that 9% growth. What would you do?
So I can't. So for the first point, I'm. I don't know. Is if we're talking globally, it's a very strong potentiality. I can't speak on a global scale at all. In the UK, it's very tough to see any industry growing by 9% at the moment with the economy and how bad the job market's looking. But to reach that goal, it'd be twofold things. So one, you got to get early professionals into their careers. So I'm applying for placements at the moment. So it'd be a big push on companies to do placement years and whatnot. Like get young people in with experience early on, give them a passion for engineering, strong grad roles, strong training schemes. And the other would be a focus on new technologies. So the established technologies aren't going anywhere. They have been profitable. They are profitable. They will be profitable, but you're reaching a point of saturation with them where they're always going to need people working there. But it's not, you can only have so many people working there at a time. And if you want 9% growth, you have to have new jobs. And a lot of those new jobs are going to come from new technologies, new fuels, new water treatments, new energy delivery methods, new chemical product processing plants. So that would be my other focus. So it'd be early career development and then trying to quickly build on new technologies.
Yeah, you've also got to incentivize people, like we've been saying throughout our conversation.
Yeah.
Yeah. It's also whether or not people would, even if you showed them all the compensation and benefits, some might just turn around and say, nah. Which is going to lead to my next question. Why do you think some people don't become chemical engineers and why some do? Because that's something you can really test for. You might have someone on paper who should become a chemical engineer and don't, and then you get someone who shouldn't but does.
I think with most things, it's passion for a subject. So I'm quite lucky. Chemical engineering, when you boil it down, it's a lot of maths, physics, chemistry. I like maths, physics, and chemistry, so it's a natural choice for me. But say like in school, I was very good at biology, so I could have gone and done something more biology focused, but I didn't want to because the passion for it wasn't there. And you'll have It's like people on my course. You'll have people that like are doing the chemical engineering degree because they're good at the technical skills and they're good at the degree and the learning process itself, but they don't have passion or even a like desire to be a chemical engineer. Whereas you'll have people on the course that struggle, but they love the subject. So it's that thing where it's not a black and white thing. It's sort of combination of skills and motivation. And some people will have all the skills in the world for it, but they've got no motivation to do it. And some people will have below average skills, but will become chemical engineers through pure motivation for it.
You reminded me of Serena Williams, the tennis player, because they did a thing on her. I can't remember what they did, but basically, she hit all the markers to get to where she is today. So she was naturally good at tennis, but then she had the desire and willpower to get better at tennis. Because it also reminds me of something else that Jocko Willink said, where this guy's basically I'm not sure. I'm a bit confused myself. He's either ex-military or he's still in the military, but he does his own thing on the side. But he said you can take two people from the same background, and you don't know why. But one would pass basic training in the military, and the other one won't. So I think there's a bit of that combination where it's just. It's a bit like Dungeons and Dragons. You roll the dice, and then whatever numbers it lands on is the outcome. I think it's the same for the person, if that makes sense.
Yeah. It's same dice, same board, but you roll it twice, you get two different numbers, basically. Yeah, okay, I get that.
Also, your hopes for not just the chemical engineering industry, but your plans going into it in the future post uni.
So short term, I'm applying for placements next year. I'm not particularly fussed at what industry I go into for those placements. I'd just like to get a year's worth of experience, then go back, complete my final year, get my integrated masters, and then it's just a big push on grad roles, really. Try and get a grad role, try and get the required training to become a chartered engineer. And I think once I get to the stage where I'm chartered, it's then just developing my skill, continuing to develop my skills, continue on professional development, and just seeing where it takes me, really.
James Graves, everyone. Have you still got the same contact information as you did last time, or have they changed since we last spoke?
As far as I know, nothing's changed from last
time.
time.
Yeah, because you had LinkedIn, didn't you?
Yeah, still do.
But check him out, and hopefully James gets where he wants to be.
Thank you very much for having me.
Likewise. If you enjoyed watching this episode whilst having James Graves back on the show, then I know that you will enjoy his first appearance over here. Oh, and don't forget to check out one of the clips from his first episode as well.